This chart comes from page 2 in your reference table, the electromagnetic spectrum. A couple of things to note here. The top of this chart indicates the wavelength, which is our lambda. The bottom indicates our frequency, and I know that it's frequency and wavelength based on the units that are there. If you look at wavelength, you're starting out on the left with 10 to the negative 13. And as you move to the right, you end up with 10 to the 4, which means that my wavelength increases as you move over to the right. If you look at frequency, you're starting out with 10 to the 21 on the left, and you're moving over to 10 to the 5th. Your frequency as you move to the right decreases. This makes sense based on our formula V equals frequency times wavelength, where F and lambda have an indirect relationship. So as frequency gets smaller, wavelength should get bigger. Another thing to note, if we look at the visible light is cut out right from this section right here. And as you look at visible light, notice that the exponent that's there is 10 to the 14. 10 to the 14 aligns with frequency, not with the wavelength values. So all visible light is measured, given to you, your frequency values. So how do you read this chart? Well, if you look at red, for instance, red starts out right over here at 3.84 times 10 to the 14 hertz, and it goes all the way up to 4.82 times 10 to the 14 hertz. So any value between those two numbers would result in red light. So say you had a value of 6.2 times 10 to the 14. Well, you look, 6.2. 6.2 falls between 6.1 and 6.59, which means 6.2 times 10 to the 14 would result in blue visible light. So let's see some problems here. Let's erase some of this stuff so that we can do some of this work. All right. So first, the table above gives the range of frequencies for visible light, 7.69 times 10 to the 14 hertz for violet, down to 3.84 times 10 to the 14 hertz for red. Use the given quantity for speed of light in a vacuum and the data above to calculate the range of wavelengths for visible light. So let's start with violet. To be able to solve for our wavelength, we are going to use our V equals frequency times wavelength formula, where V is 3 times 10 to the 8 meters per second for all of our electromagnetic waves. The frequency, they tell us right in the problem, is 7.69 times 10 to the 14 hertz, and we are solving for wavelength. The wavelength for violet is 3.9 times 10 to the negative 7 meters. We could do the same thing for red. Solving for red, we have 3 times 10 to the 8 meters per second, again, for our speed. The frequency is 3.84 times 10 to the 14 hertz. And we are solving for wavelength. Wavelength for our red light is 7.81 times 10 to the negative 7 meters. Which color of light has the shortest wavelength? Well, clearly, from our numbers, it's violet. Listed below are a set of photons, and photons are particles of light. First, tell which type of measurement each is, then which family of electromagnetic radiation the photon belongs to. So the first thing that we want to do, we want to get all of these values in terms of scientific notation. So if you look at the first, letter A, 500,000 hertz is really 5 times 10 to the 5th hertz. You cannot use the electromagnetic chart unless your values are scientific notation. B through D are all given in terms of scientific notation. So if we look at letter E, 200 meters is really 2 times 10 to the 2nd meters. So now, the first thing we do is look to see the unit as well as the exponent. So we look at letter A, we have 10 to the 5th hertz. So we go up to hertz, which is our frequency. We go 10 to the 5th, which is right over here. And you literally just drag your pencil to that piece, to that section of 10 to the fifth. And wherever that line falls is a possibility of what kind of wave this could be. So here you're able to have radio waves, you can have long radio waves. Either answer is accepted. So we'll say radio waves. If you look at the next, we have 10 to the negative 9 meters. So now, if we look at 10 to the negative 9 in our meters, that's right here, and we go down, this could be X-rays or ultraviolet. I'm going to say X-rays. Either one would be accepted. On a question, a multiple choice, or a regions-based question, or a CASA learning question, you won't have options. It will be very clear-cut what your answer is going to be. For letter C, 10 to the 13 hertz, we go up 10 to the 13. 10 to the 13 hertz is frequency. Bring our line up, and these are clearly infrared. Then we look at 4.5 times 10 to the 14 hertz. So we go 10 to the 14 hertz. Well, let's get rid of some of these lines here so we can see what's happening. If we look at 10 to the 14, notice that visible light is also given to you in 10 to the 14, as is infrared. So we need to be more specific. So this is 4.5 times 10 to the 14. So we now have to look at visible light, and we say, okay, well, 4.5, where does that fall? So 4.5 falls between 3.84 to 4.82, which means that 4.5 is red visible light. The last 10 to the second meters, we go up 10 to the second, right over here, bring it down, and this is radio waves. So now we have an electromagnetic wave with a wavelength of 5 times 10 to the negative 9 meters traveling through outer space. What is the speed of this wave? Well, all you need to know is that it's an electromagnetic wave, and this electromagnetic wave traveling through outer space is the speed of light, 3 times 10 to the 8 meters per second. That's our variable C. Determine the frequency of this wave. Well, in order to determine the frequency, I'm going to use my V equals frequency times wavelength formula. V is 3 times 10 to the 8 meters per second. Frequency is what we are solving for, and wavelength is 5 times 10 to the negative 9 meters. Solving for frequency, we end up with 6 times 10 to the 16 hertz. In what part of the electromagnetic spectrum is this wave found? Well, we have 10 to the 16 hertz, so we go back to our chart. Looking at 10 to the 16 for our hertz, that falls right over here, and that is ultraviolet. For number 2, an electromagnetic wave with a frequency of 6.2 times 10 to the 14 hertz is passing through unknown substance that has an index of refraction of 2.4. In what part of the electromagnetic spectrum is this wave found? So we have 6.2 times 10 to the 14 hertz. So you go up to our chart. 6.2 times 10 to the 14. 6.2 falls between blue and violet, which means that this is blue. I meant 6.1 and 6.59, which means that this is blue visible light. Determine the speed of this wave in the medium. Well, I'm looking for speed. I know my n. I know frequency. And always, this is an electromagnetic wave, so we know the speed of light. So I can use n equals c over v, where n is 2.4. C is always 3 times 10 to the 8 meters per second, and v is what we're looking for. Put it over 1, cross multiply, and you should end up with 1.25 times 10 to the 8 meters per second. For letter C, calculate the wavelength of this wave in the medium. So here I can use V equals frequency times wavelength, where again, my V is coming from my problem. So 1.25 times 10 to the 8 meters per second. My frequency given to me is 6.2 times 10 to the 14 hertz. And we are solving for wavelength. Wavelength, if done correctly, should be 2.02 times 10 to the negative 7 times to the negative 7 meters. Number 3, bees have specially adapted eyes that can detect electromagnetic radiation outside of what humans refer to as visible light. Some flowers that bees visit have colorations that are invisible to humans and yet match this amazing evolutionary development in bees. Bees also use these specially adapted eyes to aid them in navigation when it's cloudy. This type of radiation has a somewhat higher frequency than that of visible light. What part of the electromagnetic spectrum are these bees able to see? Well, they tell us that it is a higher frequency than visible light. So, we go up to our chart. Visible light is 10 to the 14. We want a higher frequency. The higher frequency would be ultraviolet. You know that you can get sunburned even on a cloudy day, and that comes from ultraviolet radiation. So bees are able to see with ultraviolet. For number 4, many snakes have a set of sense organs built into a set of pits in the tip of their snout. These organs enable snakes to hunt at night by sensing the heat that other animals emit. What part of the electromagnetic spectrum do these snake organs use? Well, you may already know this just by the word heat. Snakes are able to see using infrared radiation.